There are over 5,000 minerals discovered so far, and many of them are impossible to identify in hand samples. So to identify these minerals, we need to use the petrographic microscope. The petrographic microscope has two modes, conoscopic and orthoscopic. You can also change the number of polarizers used, either just using the lower polarizer, which allows east-west vibrating light through to produce PPL, or the lower in addition to the upper analyzer, which allows north-south vibrating light through, so you're able to get cross-polarized light. This video is part 2 of the optical properties of minerals, and focuses on observations in cross-polarized light. If you haven't watched part 1 on the basics of optical mineralogy and observations in plane polarized light, click the card in the top corner, watch that, and then come back, as part 1 lays out the basics that we'll build on in this video. Cross-polarized light allows us to see how light is refracted within the mineral. Remember from part 1 how minerals are either isotropic or anisotropic, and that anisotropic minerals cause plane polarized light entering to undergo double refraction and be split into two rays. That's what we're working with now. When it comes to isotropic minerals, XPL is not that helpful, as these minerals don't cause double refraction, and so are always dark under XPL, as the two polarizers are perpendicular. So if the plane polarized light's vibration direction isn't changed, the light is not able to pass through the second polarizer. In double refraction, the light ray is split into two rays, with specific vibration directions that are perpendicular to each other. These two rays also have different velocities while moving through the crystal, due to compositional and structural differences. This change in velocity results in a lag between the slow and fast ray emerging from the crystal, which causes a difference in the refractive index of the two rays, with the slow ray having a higher refractive index. Remember, the refractive index is the velocity of light in a vacuum divided by the velocity of light in a crystal. The difference between the refractive indexes of the two rays results in the birefringence of the mineral, the refractive index of the slow ray minus the refractive index of the fast ray. The maximum birefringence is a diagnostic property of a mineral. The birefringence is measured through the color of the crystal under cross-polarized light. Just make sure to rotate the stage so the mineral isn't black. We'll get into that next. To quantify the interference colors, we compare the color observed and the thickness, which is normally 30 micrometers if in a SEN section, with the Michel-levy interference color chart. Find the color observed and the thickness, then where they intersect, follow the diagonal line up to where the birefringence is labeled. You may have to test multiple grains to find the maximum birefringence, as this can change based on how the crystal is cut, once again due to the compositional and structural differences. Anisotropic minerals cause double refraction in almost every direction. However, in a given mineral, there are either one or two directions where double refraction does not occur. These directions are known as the optic axes, the directions in which light traveling parallel to double refraction does not occur. If a crystal is cut perpendicular to this axis, it will behave isotropically under XPL, as all light will be traveling parallel to the optic axis. If this is the case, just switch to a different grain. Minerals in the tetragonal, hexagonal, and rhombohedral crystal systems have just one optic axis. These are known as uniaxial minerals, while minerals in the triclinic, monoclinic, and orthorhombic crystal systems have two optic axes. These are known as biaxial minerals. The next property observed under cross-polarized light is extinction. Remember when finding the interference colors, how on some rotations of the sage the mineral was dark or black? That was because the mineral was in its extinction position. In a 360-degree rotation of an anisotropic mineral that's not cut perpendicular to the optic axis, there are 4 positions where the mineral is extinct, which we can test by rotating the stage of the microscope. Based on these positions, there are multiple types of extinction, which we look for relative to cleavage traces, or, if there's no cleavage traces present, elongation. These types include parallel extinction, such as in this biotite, where the mineral is extinct when its cleavages are oriented either east-west or north-south. In this case, the extinction angle, the angle from the north-south parallel to its extinction position, is 0 degrees. Then there's inclined extinction, where extinction occurs when the cleavage traces are inclined relative to east-west or north-south. In inclined extinction, the extinction angle can change based on the mineral being measured. To find the extinction angle, line the mineral's cleavage, or elongation, along the north-south parallel, then rotate the stage until it's extinct. Subtract the starting measurement from the extinction measurement, and there's your extinction angle. There's also symmetrical extinction, such as in this calcite, where the mineral is extinct when the east-west or north-south directions bisect the 2 cleavage traces. Note that a cross-section of the mineral is required to observe this phenomenon. Some minerals, namely quartz, exhibit undulatory extinction, where different parts of the mineral go extinct at different times during the rotation of the stage. This is due to deformation of the mineral. Micas, such as biotite, can exhibit bird's eye extinction, where little specks of light show through the extinct mineral. This is not an inherent property of the mineral, but an artifact of the grinding during thin section creation, which causes bits of the mineral to flake off due to its platy structure. This is very helpful for telling biotite from lateral sections of hornblende. Some minerals can also exhibit twinning, which is when 2 crystals form together related through some symmetry element. These can easily be observed in cross polarized light due to the twins going extinct at different times. There are many types of twinning, such as these Carlsbad or simple twins in sanidine, which is a type of feldspar, or these albite twins, which make up the diagnostic polysynthetic twinning in plagioclase. Alkali feldspars such as microcline also exhibit tartan twinning, which looks like this weaved structure, but is actually a bunch of tiny lens-shaped structures due to a combination of albite and pericline twins. Some minerals also have cyclic or sector twinning, where they're rotated around an axis. The next property is the sign of elongation. To find the sign of elongation, you first need an elongated grain, such as this sillimanite. Next, bring the grain to extinction by rotating the stage. Then rotate the grain 45 degrees. I like to rotate it so it's elongated along the southwest to northeast direction, but either way works. Then, we insert the gypsum accessory plate. The gypsum in this plate is anisotropic, so it refracts the light to a specific degree. The slow vibration direction is signified by the Z on the plate. Your mineral grain should change color due to the extra light refraction. If the interference color increases in order, such as a first-order gray becoming a blue color, that means the 2 slow directions are parallel, resulting in addition of retardation. But if the interference color decreases in order, such as a first-order gray becoming a yellow color, as the Michel-levy chart is reflected along 0, this means the slow ray of the plate is parallel to the fast of the mineral grain, resulting in the subtraction of retardation. We can then use this to describe the sign of elongation. If the slow ray vibrates lengthwise, we call it length slow. But if the fast ray vibrates lengthwise, we call it length fast. That sillimanite from before is length slow, due to going from a gray to a blue when the elongate direction was parallel to the slow ray of the plate. These are diagrams of the indicatrix of uniaxial minerals. These diagrams show the refractive index of different axes in the mineral, and are important to understand the optical property known as the optic sign. This is not the same as the sign of elongation, so do not mix the two up. As you can see, uniaxial minerals have two different indicatrices. Notice the extraordinary ray vibrates vertically along the C crystallographic axis, and this is the same direction of the optic axis, so no double refraction occurs along C. When the optic sign is uniaxial positive, the refractive index of the extraordinary ray is larger than that of the ordinary ray, which vibrates horizontally, so the indicatrix is a prolate ellipsoid. While when the optic sign is uniaxial negative, the refractive index of the extraordinary ray is smaller than that of the ordinary ray in an oblate ellipsoid. And therefore, how the mineral is cut will change the directions the rays vibrate in a plane. When finding the optic sign, the best grains are cut perpendicular to the optic axis, or at a low angle to the optic axis. These grains have a low birefringence, so should be easy to pick out. Once you've centered on the chosen grain, switch to the 40x objective lens, insert the Bertrand lens, and insert the condensing lens to use conoscopic mode. You should see an interference figure, such as a centered cross, standard of a uniaxial optic axis figure, or an off-centered cross if your grain is at a low angle to the optic axis. You may also just see a straight line. If this is the case, find a different grain. While you are technically able to use that one, it's not suggested, especially if it's your first time. You may also find something like this, where most of it's black. This is an optic normal interference figure, cut parallel to the optic axis, and exhibiting the maximum birefringence. This one is actually useless, so find a new grain. Back to the optic axis figure, the dark cross is made of the isogyres, due to the mineral in these sections being extinct, which is due to how the Bertrand and condensing lenses refract the light. Where the two isogyres intersect, you'll find the melatope, which is where the optic axis emerges. You may also see these colorful rings. These are known as isochromes, and they just mean your mineral is either thicker or has a high birefringence. We can just ignore them. In the circular section, the two rays vibrate like this, where the extraordinary ray vibrates radially, and the ordinary ray vibrates tangentially. Then you'll insert the gypsum accessory plate and pay attention to the northeast quadrant. Like with the sign of elongation, if the interference color increases in order, that's addition of retardation, so the extraordinary ray's refractive index is greater than that of the ordinary rays, which makes the mineral uniaxial positive. But if it decreases in order, that's subtraction of retardation, and the refractive index of the ordinary ray is greater, making the mineral uniaxial negative. You can remember this using burp, blue upper right means positive, and yearn, yellow upper right means negative. The Biaxial Indicatrix is quite different, as it has two optic axes that intersect in the middle, while the BXA, or acute bisectrix, and the BXO, or obtuse bisectrix, bisect the two angles created by the two optic axes. The three crystallographic axes, A, B, and C, can all be equal to one of the three vibration directions of X, Y, and Z. X is the fastest of the three, while Z is the slowest. The optic sign of biaxial minerals is determined by which of BXO or BXA bisects the 2V angle, and therefore whether BXA or BXO have the larger refractive index. If BXO has the lower refractive index, making BXA the Z or slow vibration direction, the mineral is biaxial positive. While if BXA has the lower refractive index, making BXO the Z, or slow vibration direction, the mineral is biaxial negative. We can use interference figures for biaxial minerals as well, but these look quite different. Just like with uniaxial minerals, insert the Bertrand and condensing lens with the 40x objective lens in XPL while centered on the target grain to find the interference figure. This time we'll be looking for the acute bisectrix, or BXA, interference figure, which is cut perpendicular to the acute bisectrix. Again, there's two isogyres, which actually come together and move apart as you rotate the stage. These isogyres are curved, and there's two melotopes where the optic axes emerge at the corner of each isogyre. The Y vibration direction stays the same in each section, as seen on this diagram. However, in the BXA figure, the middle section has BXO perpendicular to Y, but the outer two sections have BXA perpendicular to Y. Again, insert the gypsum accessory plate, then look at the middle section. If addition occurs such that the middle is blue, BXA equals X, the fast direction, so the optic sign is biaxial negative. And again, if subtraction occurs such that the middle is yellow, BXA equals Z, the slow direction. So the optic sign is positive. You can remember BAM-YIP, biaxial middle yellow is positive, and BAM-BIN, biaxial middle blue is negative. The optic axis interference figure, cut perpendicular to the optic axis, usually works for the biaxial minerals as well. But it's basically just an off-center BXA figure, so based on the curvature, you can extrapolate the other isogyre and can know which side is the middle. The one exception to this is if the mineral has a large 2V angle, as then the isogyres will basically be straight, so extrapolation is impossible. You can, however, use the optic axis interference figure to estimate the 2V angle, as seen in this diagram. A 2V of 0 degrees is a uniaxial mineral, as then there's just a single optic axis. As you increase the 2V angle from there, the isogyres become further apart at their maximum and become straighter until at 90 degrees you just have a straight line, which is useless for finding the optic sign. The 2V angle can be used to distinguish really similar minerals, but usually using other optical properties is easier and more efficient. Biaxial minerals have two other interference figures. The BXO figure, which is cut parallel to the optical plane, which contains both optic axes, which is useless for finding the optic sign. And again the optic normal figure, which displays the maximum birefringence and is cut perpendicular to the optic normal, which is parallel to the optic axis. Just like in uniaxial minerals, the isogyres cover most of the figure, and it's useless for finding the optic sign, so just toss that one out too. Some minerals can also exhibit zoning, such as in this plagioclase, where zoning occurs from the core to the rim. This is best observed in cross polarized light, and is due to compositional variation within a single crystal, usually due to specific conditions such as rapid cooling during crystallization. This results in these rings of differing composition. In plagioclase, it's due to differing amounts of albite, which is the sodium end member, and anorthite, the calcium end member. Some minerals may also exhibit exsolution, which is just small crystals of another mineral embedded in the crystal due to an incomplete solid solution. This is common in alkali feldspar such as this persite, that contains Exsolution lamellae of plagioclase. And those are all the main optical properties of minerals observed under transmitted light with the petrographic microscope. Minerals such as opaque oxides or sulfides, which don't transmit light, and small clay minerals, which are too small to identify with the petrographic microscope, require different techniques to analyze. If you enjoyed this video, make sure to subscribe, like, share, and if this video helped you, leave a comment. And maybe check out one of these other videos.